Right now, the blood running through your veins, the air filling your lungs, and, well, even the device you are using to listen to this right now, they all share one kind of chaotic underlying trait.
They do, and it's that absolutely none of them are pure.
Exactly. Like, we live in a universe that just desperately wants to mix things up, you know?
Yeah.
Purity is essentially a myth.
Or at least a very temporary state, one that requires just an immense amount of energy to maintain.
Yeah, because it's a constant battle against entropy, right?
Oh, totally. Nature's default state is just a chaotic jumble. I mean, if you leave things alone in the universe, they degrade, they combine, they tangle up.
Which brings me to the fundamental question of our deep dives today. I want you, the listener, to picture a field of sugarcane.
Okay, picture that.
You've got these massive, tough, fibrous green stalks swaying in the wind, right? They're covered in dirt. There's insects all over them.
Total mess, biologically speaking.
Right. But now, walk into your kitchen, open your pantry, and look at a bowl of processed sugar.
The contrast is pretty mind-boggling.
It really is. You are looking at pure, perfectly sweet, white, crystalline geometric structures. So how in the world do we force that dirty, chaotic green stalk to yield that pristine crystal?
It's basically a magic trick, but it's science.
Yeah. And to raise the stakes considerably here, imagine you're in a rural clinic somewhere. A doctor takes a single tiny drop of your blood.
Which is a super complex soup, you know. It's plasma, cells, proteins, water.
Exactly. And within minutes, from that one microscopic chaotic jumble, they can isolate a pathogen and diagnose a complex disease like malaria.
We take these everyday miracles completely for granted, like totally.
We really do. We just expect the sugar to be in the bowl.
Right. And we expect the medical test to yield an instantaneous answer. But the bridge between the raw, messy material of the natural world and that refined final product, it's built entirely on the science of physical and chemical separation.
It's not just about, like, filtering dirt out of water.
No, not at all. It is about understanding the fundamental physical properties of matter. So things like boiling points, density, molecular geometry, electrostatic charges.
And kind of weaponizing those properties to untangle the universe, right?
Weaponizing is a great way to put it. Yeah.
So that is our mission for today. We're going to deconstruct the science of untangling mixtures.
We're going to bridge the gap between, the ingredients on your kitchen counter and those massive industrial petroleum plants that power our cities.
And the life-saving medical devices used in, like, the most remote villages on Earth.
But to understand how to take a mixture apart, we first have to understand how the universe actually puts it together.
Right, let's start at the foundational divide. Because in chemistry, every mixture basically falls onto one side of a Grand
A
Canyon.
very clear divide, yes.
On one side, we have homogeneous mixtures, and on the other, heterogeneous mixtures.
And the distinction really boils down to the concept of uniformity, like at a molecular level.
Okay, let's tackle homogeneous mixtures first.
So the prefix homo means the same. In a true homogeneous mixture, which we also call a solution, the composition is absolutely flawlessly uniform throughout the entire volume.
Meaning every part is exactly the same as every other part.
Exactly. Think about dissolving sugar into a glass of pure water. You stir it until it disappears.
It looks like plain water again.
Right. And those sugar molecules, they don't just float around in little clumps. The kinetic energy of the water molecules literally batters the sugar crystals apart.
Oh, wow. So it's a violent microscopic process.
Very. It breaks their intermolecular bonds. And then water molecules surround every individual sugar molecule.
So they're evenly dispersed on, like, a totally microscopic scale.
Yes. Every single sip of that water is going to have the exact same ratio of sugar to water.
So the first sip at the top of the glass is chemically identical to the last sip at the very bottom.
Yeah, and because those individual sugar molecules are infinitesimally small, gravity cannot pull them down.
Wait, really? Never.
Never. They will never settle out of the water on their own, no matter how long you leave that glass sitting on your kitchen counter.
So they act as a single uniform phase of matter.
Precisely. Some other common examples would be white vinegar, which is just acetic acid uniformly dispersed in water.
Okay.
Or even the air we breathe right now. It's a homogeneous mixture of nitrogen, oxygen, argon, and carbon dioxide.
To give this a tactile analogy, a homogeneous mixture is kind of like a perfectly smelted metal alloy, right?
Yeah.
Like bronze.
That's a great example.
You melt copper and tin together, And once it cools, you can't point to a spot on the bronze shield and say, oh, that right there, that's pure tin.
Right, because the metals have essentially become a new unified material.
But then we cross the canyon to the other side. Heterogeneous mixtures.
Hetero meaning different. These lack that molecular uniformity.
So it's chunkier.
Basically, yeah. Instead of molecules intimately surrounding each other, you have distinct, separate domains of different substances coexisting in the exact same space.
So instead of a perfect bronze alloy, a heterogeneous mixture is more like a concrete aggregate.
Yes, except
When you pour concrete, you have cement paste, sand, and large chunks of gravel. And even after it sets, you can look closely and clearly see the individual rocks embedded in the cement.
Right, the parts remain distinct. Structurally, they have totally different properties.
Or, if we look at a liquid example, shaking a bottle of oil and vinegar dressing.
Oh, that is a classic example. You apply mechanical energy by shaking the bottle, right?
Yeah, you shake it up really hard.
And that forces the oil to break up into little droplets dispersed in the vinegar, but they haven't dissolved.
The molecules haven't bonded or surrounded each other on that molecular level.
Exactly. And the moment you stop shaping, what happens?
It separates.
Right. The differing densities and the lack of chemical affinity cause those oil droplets to aggressively seek each other out.
They merge and float right back to the top. The mixture stubbornly separates itself.
It refuses to stay mixed.
Okay, I understand the clear-cut examples. Salt water is homogeneous, oil and water is heterogeneous. But I want to talk about where our eyes fail us.
Oh, this is the fun part?
Because sometimes nature wears a disguise. Let's take a glass of milk.
Okay.
If I pour a glass of whole milk, it looks like a pure, flawless white liquid.
It does.
It doesn't have chunks of gravel in it. It doesn't separate into distinct layers if I leave it on the dining table for an hour.
Nope.
So my brain automatically categorizes that as a homogeneous solution.
And your brain would be completely, totally wrong.
Is it?
Oh, yeah. Milk is one of the most fascinating tricksters in chemistry. It belongs to a subcategory of mixtures called a colloid.
A colloid.
Right. To the naked eye, it looks uniform, but under a microscope, it is actually a highly crowded suspension of fat globules and protein clusters floating in water.
Wait. If it's full of fat globules, why doesn't it behave like the salad dressing?
That's the logical next question.
Why doesn't the fat instantly float to the top and form a solid layer of oil like the vinaigrette did?
It comes down to the size of the particles and the presence of emulsifiers.
Okay, break that down for me.
The fat particles in milk are much larger than individual dissolved sugar molecules in a solution, but they are still small enough, typically between like 1 and 1,000 nanometers, that the constant random thermal motion of the water molecules keeps them suspended.
So the water's knocking them around constantly.
Exactly. It's called Brownian motion. The water molecules continually knock them around so they can't settle.
And what about the emulsifiers?
Plus, proteins in the milk act as a kind of chemical wrapper around the fat.
A wrapper.
Yeah, preventing the fat droplets from sticking together and merging into a larger layer that would float to the top.
So it is essentially a microscopic concrete aggregate, but the rocks are just chopped up so finely that my eye can't resolve the individual pieces.
That is a perfect way to visualize it.
But how do we actually prove that without, a high-powered electron microscope?
We unmask the disguise using the physics of light. We use something called the Tyndall effect.
I've actually tried this at home, and it feels like a parlor trick.
It really does. It's super visual.
You take a standard laser pointer, you shine it through a glass of pure salt water, a true homogeneous solution. What happens? Almost nothing.
Right, nothing.
The beam passes through the liquid invisibly. You see the dot hit the wall on the far side of the glass, but the liquid itself remains totally transparent.
And that invisibility tells us everything about the molecular structure.
How so?
In that true solution, the dissolved salt ions are around 0.1 nanometers wide. They are significantly smaller than the wavelength of visible light.
Okay.
So when the photons from the laser travel through the water, they essentially don't even see the salt. They sail right past those tiny obstacles without hitting them.
But then you take that exact same laser pointer and shine it through the glass of milk.
And boom!
Suddenly the entire path of the beam lights up. It looks like a glowing, solid, green or red lightsaber suspended inside the milk.
And that glowing shaft of light is the Tyndall effect.
So what am I actually seeing there?
Yeah. You are seeing the physical collision of photons with matter. Those suspended fat and protein globules in the colloid are large enough. They're approaching the wavelength of the light itself that when the laser hits them, they act like millions of microscopic mirrors.
Oh, wow. So they're bouncing the light everywhere.
Exactly. They shatter the organized beam of light, scattering those photons in every possible direction, including sideways, right out of the glass and into your retina.
It is a super visceral reminder that visual deception is everywhere.
It really is.
Just because a liquid looks smooth doesn't mean the matter inside it has actually merged. You are drinking a microscopic obstacle course.
I love that phrase, a microscopic obstacle course. And it also tells us that identifying what is in a mixture, whether it's a solution or colloid, is really only the first step.
Right, because once we know what we are dealing with, the science of mixtures demands that we master how much of each substance is present.
Yes, which introduces the concept of concentration.
Concentration. It's a word we throw around a lot in daily life.
Like concentrated orange juice.
Or concentrated laundry detergent, yeah. But in chemistry, it's the exact measurement of the solute, the substance being dissolved, relative to the solvent, the substance doing the dissolving.
It is the mathematics of the mixture. And honestly, we cannot understate the real-world stakes here.
Really?
Yeah, concentration is not just a lab parameter. It is the invisible tightrope between a miracle and a catastrophe.
Okay, give me a life-or-death example.
Let's look at the treatment of severe dehydration, particularly in regions battling waterborne diseases like cholera.
Okay, cholera is brutal.
It is. And the primary defense against cholera mortality isn't antibiotics, believe it or not. It is a remarkably simple mixture called oral rehydration solution, or ORS.
The little packets you mix into water.
Exactly. It has saved an estimated 50 million lives since its invention. But ORS is not just random sweet, salty water.
Yeah.
No, it requires a hyper-specific concentration. Typically a precise ratio of sodium chloride and glucose dissolved in exactly 1 liter of clean water.
I want to pause on the mechanics of that. Because if someone is dying of dehydration, why can't we just give them a glass of water with a giant scoop of salt and a giant scoop of sugar?
You'd think so, right?
Surely getting those electrolytes into them is the goal, regardless of the exact ratio.
If you do that, you might actually accelerate their death.
Right. Seriously?
Seriously. The human intestine is a highly regulated, semi-permeable membrane. When cholera toxins attack the gut lining, the body actively dumps water out of the tissues and into the intestines, causing catastrophic fluid loss.
Oh, so they're losing water rapidly.
Yes. And to reverse this, we have to trick the intestinal cells into pulling water back in. This relies on a specific cellular gateway called the sodium-glucose cotransporter.
A cellular gateway. Okay, how does the mixture unlock it?
This specific biological gateway only activates when it encounters 1 molecule of sodium and 1 molecule of glucose simultaneously.
Oh, wow. So it's literally a lock that needs 2 keys at the same time.
Exactly. When that exact 1-to-1 molecular pairing locks into the cellular receptor, the gateway opens, pulling both the salt and the sugar into the bloodstream.
And then what about the water?
Because of the laws of osmosis, water aggressively follows those molecules back into the body, rapidly rehydrating the patient.
So if your concentration is wrong, if you put in too much salt and not enough sugar, the gateways don't trigger.
Right.
The salt just sits in the intestine.
Worse than sitting there. A highly concentrated, overly salty mixture sitting in the gut will actually draw more water out of the patient's tissues through osmosis.
Oh my God, so it worsens the dehydration.
It does. The medical efficacy of ORS is entirely 100% dependent on maintaining that exact scientifically calibrated concentration.
That perfectly illustrates the danger of the more is better fallacy.
Oh, humans fall for that all the time.
Human instinct screams that if a medicine works, a double dose will work twice as fast.
Which is almost never true.
Let's pivot to an industrial example of that exact same fallacy. Think about commercial agriculture.
Okay, farming.
A farmer has a devastating aphid infestation, wiping out a critical crop. They have a pesticide powder that needs to be dissolved in water before spraying.
Right.
The temptation to double the concentration of the pesticide to ensure every single bug dies must be overwhelming.
It is a super common instinct, but chemically it's a disastrous miscalculation.
Let's map out the cascading failures of that decision.
Sure, if the farmer uses a concentration that is too low, the application is useless. The aphids survive and the crop is lost.
But if they double the concentration, creating a highly saturated pesticide mixture.
They cross the line from protection to indiscriminate destruction.
Right, because pesticides aren't smart bombs. They're just toxic chemicals.
Exactly. At a hyper-elevated concentration, that chemical mixture will cause phytotoxicity.
Phytotoxicity.
Yeah, it literally burns the leaves and stems of the very crop the farmer is trying to save.
So they kill the crop themselves.
Yep. And furthermore, the soil cannot absorb that level of chemical density. The excess concentrated pesticide leaches into the earth, exterminating the microscopic mycelial networks and beneficial bacteria that actually make the soil fertile.
And when the next rain comes.
That dense chemical payload runs off into the local water table, causing massive algal blooms or fish die-offs miles downstream.
So the correct concentration is the only thing standing between a localized agricultural solution and a systemic environmental collapse.
It requires absolute control over your materials.
So let's say we have mastered this control. We have our perfectly concentrated homogeneous solution.
Okay.
We have dissolved a solid solute perfectly into a liquid solvent. The ultimate challenge of our deep dive is reversing the clock.
Unmixing it.
Exactly. How do we take that seamlessly blended solution and extract the solid back out in its absolute purest form?
We use the architecture of nature itself. We use a purification technique called crystallization.
Crystallization.
It is perhaps the most visually stunning process in chemistry, and it operates entirely by manipulating a physical property called solubility.
Solubility, meaning how much of a solid can dissolve in a given liquid.
Right. But solubility is not static. It is highly dependent on thermal energy.
Heat changes everything.
It really does. Let's walk through the exact laboratory mechanics of purifying a deeply contaminated batch of copper sulfate.
Okay, set the scene.
Copper sulfate in its pure form is a striking, translucent blue crystal. It's beautiful. But raw industrial copper sulfate is often a dull, powdery, blue-green mess, heavily contaminated with dirt, iron, and other chemical byproducts.
So to extract the pure blue geometry from that mess, we start by creating a hot, saturated solution.
Yes.
Take a glass beaker, fill it with water, and put it over a heat source. As the water temperature approaches the boiling point, we start dumping in our dirty, contaminated copper sulfate powder and stirring furiously.
And here's why the heat matters. At room temperature, maybe only 30 grams would dissolve in 100 milliliters of water.
Okay.
But at 100 degrees Celsius, the kinetic energy of the water is so violently active that it can tear apart and absorb massive amounts of the powder.
Like 3 or 4 times as much.
Exactly. We keep adding the powder until the water absolutely refuses to absorb a single grain more.
That is the definition of a saturated solution.
Right. But there is a crucial, easily overlooked step in the chemical protocol here. While creating this hot mixture, a chemist will carefully add just a single drop of dilute sulfuric acid to the beaker.
I was going to ask about that.
Yeah.
Because I read that in the source material and it seemed totally counterintuitive.
So?
Well, our entire goal is to purify the copper sulfate, right? So why are we actively introducing a foreign acid into the mixture? Aren't we just adding a new impurity?
No, we are adding a chemical bodyguard.
A bodyguard.
Yeah. At near boiling temperatures, copper sulfate dissolved in water can undergo an unwanted side reaction called hydrolysis.
What does that do?
The water molecules actually start breaking the copper compounds apart, forming cloudy, insoluble copper hydroxides that would completely ruin our final product.
Oh, so the water attacks the copper.
Yes. By adding a tiny, precise amount of sulfuric acid, we lower the pH just enough to chemically suppress that hydrolysis reaction.
Gotcha.
It guarantees that the copper sulfate remains entirely intact while dissolved in the extreme heat.
Okay, so the acid acts as a shield. Now we have this boiling hot, saturated, slightly acidic blue liquid.
Right.
It's full of dissolved copper sulfate, but it also has all the insoluble dirt and sand from the original raw powder swirling around in it.
Which is why our immediate next step is rapid filtration. While the liquid is still scalding hot, we pour it through high-grade filter paper.
Right, because we need to get the chunks out.
Exactly. The paper catches all the solid, insoluble impurities, the dirt, the sand, the grit. And what drips through into our clean collection beaker below is a perfectly clear, dark blue, uniform liquid.
And here is where the discipline of chemistry really comes in. You have this hot, clear liquid. To trigger the crystallization, you have to do the hardest thing for a human being to do. Absolutely nothing.
It takes so much patience. You must abandon it. You cover the beaker with a piece of filter paper to keep dust out. You place it in a quiet corner of the lab where it won't be vibrated or bumped, and you let it cool down to room temperature over many hours or even days.
Let's talk about the thermodynamics of what is happening inside that beaker as it sits in the quiet lab.
Okay.
As the thermal energy slowly bleeds out of the glass into the surrounding air, the water molecules lose their frantic kinetic energy. They slow down.
Right.
And as they slow down, their capacity to hold all that dissolved copper sulfate plummets.
The water literally begins to evict the copper sulfate molecules.
But they don't just precipitate out as a messy, chaotic powder.
No, and this is the magic part. Because the cooling process is agonizingly slow, the copper sulfate molecules are granted the luxury of time.
Time to do what?
When a molecule is evicted from the water, it doesn't just grab onto the first thing it touches. It slowly drifts until it finds another copper sulfate molecule. And due to their specific atomic shapes and charges, they lock together in a highly specific, repeating geometric pattern.
Crystal lattice.
Yes, this is a crystal lattice.
And as millions of molecules join this microscopic architecture, the lattice grows into massive, flawless, sharp-edged blue crystals that you can actually hold in your hand.
It's incredible to watch.
But what happens to the impurities, the iron and other soluble chemical contaminants that were also dissolved in the hot water? Why don't they get trapped in the crystal?
That is the genius of the crystal lattice. It is an exclusive VIP molecular club.
I love that, a VIP club.
It really is. A crystal lattice is geometrically precise. Only a molecule with the exact atomic shape and charge of copper sulfate can fit into the structural grid.
So what about an atom of iron?
The impurity molecules, like iron, are simply the wrong shape. They physically cannot bridge the gaps in the growing architecture.
So they get rejected.
Exactly. As the pure blue crystal builds its walls, it actively rejects the impurities, leaving them stranded and dissolved in the cooling liquid surrounding the crystal.
The geometry itself acts as the ultimate filter.
It does.
But this entire elegant mechanism breaks down if you lose patience, right?
And completely.
What happens if I take that beaker of boiling hot saturated solution and instead of leaving it in a quiet corner, I plunge it directly into a bath of liquid nitrogen or ice water?
You induce molecular panic.
Manic.
Total panic. The temperature drops so violently and rapidly that the water instantly loses all its carrying capacity. Millions of copper sulfate molecules crash out of the solution simultaneously.
They just drop.
Yeah, they have no time to orient themselves. They have no time to build a perfect lattice. They just pile up on top of each other in chaotic microscopic clumps.
So you don't get the beautiful crystals.
No, you end up with a sludge of tiny, deformed, powdery crystals.
And crucially, because they are just piling up chaotically, they end up trapping pockets of the dirty liquid and the impurities inside their deformed structures.
Exactly. Rapid cooling destroys purity.
Patience is literally a purifying force.
That's a very poetic and scientifically accurate way to look at it.
And what I find so compelling is that humanity understood this concept long before we had borosilicate beakers and Bunsen burners. We observed it in nature.
The historical context here is incredibly rich. Ancient coastal communities, particularly in the Indian subcontinent, harnessed these exact physical principles to extract essential survival resources from the ocean.
They manufactured two distinct grades of salt using the thermodynamics of evaporation.
Right.
The source material specifically references panga salt and karkach salt. Let's break down the macro-scale chemistry of how they made them.
Okay, to produce panga salt, the workers would trap concentrated seawater brine in shallow clay pans and light massifiers underneath them,
Okay, so boiling it.
violently introducing heat to force the water to boil away as fast as possible. The rapid removal of the solvent meant the sodium chloride molecules had to precipitate out instantly.
Just like dropping our beaker in an ice bath, the molecules panic.
Precisely the same mechanism, just driven by rapid evaporation rather than rapid cooling. Because the salt was forced out so quickly, panga salt crystallized into very fine, small, powdery grains.
It was functional, but structurally chaotic.
Right. But then they had karkach salt, which was considered superior for certain uses.
How was that different?
They didn't use fires for karkach. They simply trapped the brine in large, shallow coastal beds and let the ambient heat of the sun slowly evaporate the water over weeks or months.
They traded fire for time.
Exactly. By allowing the sun to enact a prolonged, gentle evaporation, they were replicating our slow laboratory cooling process.
So the water slowly disappeared.
And the salt molecules were given ample time to find each other, orient themselves, and build massive, coarse, highly structured geometric crystals.
Thousands of years ago, without understanding molecular lattices, they were manipulating thermodynamics to dictate the architecture of their food supply.
It's brilliant chemical engineering disguised as traditional labor.
It really is. But let's acknowledge the limitation here. Crystallization is unparalleled if you want to extract a solid out of a liquid.
Sure.
But what if our mixture doesn't contain a solid?
Then you need a different tool.
Right. What if we have two liquids perfectly blended together? Let's say I pour acetone, which is a volatile, harsh-smelling solvent used in paint thinner and nail polish remover, into a flask of water,
Okay, they're what chemists call miscible.
meaning they mix perfectly and seamlessly.
Yes, there is no visible boundary line.
I can't grow crystals out of them. A filter paper will just let both liquids pass right through. So how do we tear them apart?
When geometry and filtration fail, we turn to brute thermal force. We use distillation.
Distillation.
If crystallization is the art of manipulating solubility, distillation is the science of exploiting boiling points. It is the ultimate tool for severing miscible liquids.
Because every pure substance in the universe has a specific boiling point.
Exactly. It's the exact temperature at which it absorbs enough thermal energy to break its liquid bonds and transition into a gas.
For water, we all know it's 100 degrees Celsius at sea level.
But acetone is a much smaller, less tightly bonded molecule. It is highly volatile. Its boiling point is only 56 degrees Celsius.
Oh, that's a huge difference.
That 44-degree gap is our mechanical lever to pry the mixture apart.
Let's visualize the laboratory setup for the listener. We pour our uniform mixture of water and acetone into a round-bottomed flask.
Right.
We seal the top with a rubber stopper that has a thermometer pushed through it so we can read the internal vapor temperature. And we place the flask over a steady heat source.
Perfect setup.
I think of this process as a foot race, where the competitors have vastly different athletic abilities.
I like that.
The heat is the starting gun. As the temperature inside the liquid climbs 20 degrees, 30 degrees, 40 degrees, both liquids are warming up, but neither is boiling.
Not yet. But the moment the thermometer hits exactly 56 degrees Celsius, the dynamic inside the flask shifts violently.
Because the acetone can't take it anymore.
Right. The acetone molecules have reached their breaking point. They absorb the heat energy, shatter their liquid bonds, and vaporize.
The liquid acetone transforms into a roaring, invisible gas that rapidly rises to the top of the flask.
Meanwhile, the water molecules, which need 100 degrees to boil, are barely breaking a sweat.
They remain completely liquid, trapped at the bottom of the flask. The fast runner, the acetone, has sprinted off the starting block while the slow walker, the water, hasn't moved.
However, having acetone gas trapped in a hot flask doesn't actually help us.
No, if we let it escape into the room, we've just lost our chemical.
We need to capture the runner. And this is where the engineering of the distillation apparatus becomes vital. Attached to the side of the hot flask is a downward-sloping glass tube called a condenser.
The condenser is an ingenious piece of glassware. It looks like a thin glass tube encased inside a larger glass jacket.
Yes, the vapor travels down the inner tube.
But what is happening in that outer jacket?
We connect a rubber hose from a cold water tap to the bottom of that outer jacket and a drain hose to the top. We pump a continuous flowing stream of freezing cold water through that outer layer.
So it's essentially a water jacket.
The cold water completely envelops the inner tube, creating a brutal temperature gradient.
So this hot, 56-degree acetone vapor races out of the flask and into the condenser tube.
And the moment it hits that inner glass wall, the thermal energy is instantly sucked out of it by the freezing water jacket surrounding it.
It undergoes rapid condensation.
Yes. The gas molecules lose their kinetic energy, clump back together, and instantly return to a liquid state.
And because the condenser tube is angled downward, gravity grabs those freshly formed, perfectly pure drops of liquid acetone and guides them down the spout.
Dripping steadily into a clean, separate collection flask.
The separation is complete. You have a flask of pure liquid acetone at the end of the condenser and a flask of pure water still sitting on the burner, never having reached its boiling point.
That is simple distillation, and it is incredibly elegant.
But if we want to truly grasp the impact of this concept, we have to scale it up. A glass flask on a lab bench is one thing, but distillation is the literal engine of the modern industrial world.
It really is.
When you drive down a highway and see a sprawling petroleum refinery, a massive metal city of pipes and towering cylinders, you are looking at distillation on a planetary scale.
Planetary scale. Let's talk about crude oil.
Yeah.
When we pump crude oil out of the earth, it is incredibly useless.
That's a mess.
It is a thick, black, highly toxic, chaotic mixture of hundreds of different hydrocarbon chains, some short, some long, some heavy, some light.
You can't put it in a car.
Yeah.
You can't pave a road with it. It is just potential energy trapped in chaos.
So to untangle that chaos, refineries use towering metal structures called fractional distillation columns.
These columns can be hundreds of feet tall.
They are massive, and they operate on the exact same principle as our acetone experiment. But instead of separating two liquids, they separate dozens of hydrocarbons simultaneously based on a continuous temperature gradient.
Walk me through the architecture of that tower. Where does the raw oil go?
The crude oil is pumped into a massive industrial furnace and subjected to staggering heat around 400 degrees Celsius.
Wow, 400 degrees.
At this extreme temperature, almost the entire black sludge flash boils into a roaring, highly pressurized, complex vapor.
And then what?
That vapor is then injected directly into the very bottom of the towering distillation column.
And the inside of that tower isn't just an empty pipe, right?
No, it is lined with dozens of horizontal metal trays spaced evenly all the way to the top.
What do the trays do?
These trays have little bubble caps that allow gas to rise through them but hold on to liquid.
Crucially, the tower has an engineered temperature gradient. It is incredibly hot at the bottom, say 350 degrees, but as you climb higher and higher up the tower, it gets progressively cooler.
Right, the very top might be only 20 degrees Celsius.
So this is a multi-story sorting facility. As that complex cloud of vapor rises from the bottom furnace, it hits these different temperature zones.
Exactly. The hydrocarbon molecules with the shortest carbon chains, meaning they have the lowest boiling points and are the most volatile, they don't condense in the heat.
They stay as gases.
They blow right past the lower trays, racing all the way to the freezing top of the tower.
And at the very top, we siphon them off. These are the lightest fractions.
This is where we capture liquefied petroleum gas, or LPG, the propane and butane you use in your backyard grill or kitchen stove. They separate out as pure gases.
But the heavier molecules in that vapor cloud, the ones with slightly longer carbon chains, they can't make it to the top.
No. As they rise, they hit a tray where the ambient temperature drops below their specific boiling point. Let's say around 150 degrees Celsius.
So at that specific tray, those specific molecules lose their thermal energy.
They condense into a liquid pool on that metal tray, and a pipe simply drains that pure liquid out the side of the tower.
And what is that liquid?
That specific tray provides the aviation fuel that powers global jet travel.
And as you look further down the tower into the hotter zones, the even heavier molecules condense out.
Right. The molecules that condense around 200 degrees Celsius are piped out to become the gasoline that fuels our cars.
Further down at 300 degrees, you get the heavy, dense diesel fuel that powers cargo ships and freight trucks.
And finally, all the way at the very bottom of the tower, in the most extreme heat, there is a thick, stubborn residue of massive hydrocarbon molecules.
Chains that are like 70 or 80 carbons long.
Exactly. They never truly vaporized at all. They just melted into a heavy sludge and fell to the bottom.
And what do we do with that heavy, useless sludge?
We scoop it out, mix it with crushed gravel, and pave our highways with it. That is asphalt.
I find it absolutely staggering to realize that the highly refined, volatile jet fuel igniting at 30,000 feet and the solid black asphalt highway I am driving on were literally touching each other, chemically bound together in a puddle of ancient dinosaur sludge before we boiled them apart in that tower.
It's kind of beautiful when you think about it. Everything we build, everything we move, relies on the precision of fractional distillation.
It is the pinnacle of exploiting physical properties for human advancement.
But distillation is an energy-intensive, brute force method. It requires massive amounts of heat.
True.
What if we are dealing with a mixture that is significantly less cooperative, but doesn't require boiling to separate? We discussed miscible liquids like acetone and water. What about liquids that absolutely loathe each other?
You're talking about immiscible liquids. Let's use mustard oil and water.
Good example.
If I pour a cup of dense yellow mustard oil into a beaker of water, they refuse to bond.
They hate each other.
Even if I put an industrial mechanical stirrer in the beaker and whip it into a frenzy for an hour, the moment I turn the machine off, the physics of the universe reasserts itself.
The yellow oil will aggressively push its way to the surface, and the clear water will sink to the bottom.
This separation is driven entirely by density and buoyancy. Right.
Entirely. Water is denser. It has more mass packed into a given volume than the oil. Therefore, the less dense oil is displaced upward, floating on top.
Because they naturally separate, we don't need a boiling flask or a towering refinery column. We use an elegantly simple piece of specialized glassware called a separating funnel.
The separating funnel looks like a large inverted glass teardrop.
And at the very bottom point of the teardrop, there is a small glass valve called a stopcock that you can twist open and closed.
You pour your messy mixture of mustard oil and water into the top of the funnel, put a stopper in it, and simply mount it on a ring stand.
You just let gravity and buoyancy do all the heavy lifting.
Within minutes, the liquids sort themselves into two distinct horizontal bands. The heavy water forms a clear layer at the bottom, and the yellow oil rests perfectly on top.
You have a sharp, highly visible boundary line between the two phases.
The mechanics of the extraction are almost absurdly low-tech.
Yeah, you place an empty beaker directly under the spout of the funnel, you reach up and you slowly twist the stopcock valve open.
The heavy water at the bottom begins draining out through the narrow tube.
You stand there and watch the boundary line, that sharp division between water and oil, slowly sink lower and lower inside the glass teardrop.
It requires extreme visual concentration.
Don't blink.
Right. As that boundary line reaches the very bottom of the funnel, just as the last drop of water passes through the valve, you swiftly twist the stopcock shut.
The water is in the beaker below, and the pure mustard oil is trapped in the funnel above.
In practical laboratory settings, it's rarely that clean. Usually there is a tiny, ambiguous middle layer where a bit of oil and water are emulsified together.
A messy middle.
A good chemist will drain the bulk of the water into one beaker, then drain that messy middle boundary layer into a designated waste container to ensure it doesn't contaminate the final products.
Then they place a third, clean beaker under the funnel and drain the pristine oil.
That is the practical reality. But I want to pivot to a theoretical realm here.
Oh, I love the theoretical stuff.
The source text we are analyzing poses a brilliant thought experiment regarding immiscible liquids that forces us to test the absolute limits of this tool.
Right. Let's say you are in a cutting-edge laboratory and you synthesize two brand new, completely novel liquids, liquid A and liquid B.
Okay.
They are highly immiscible. Their chemical structures are so hostile to each other that they will never, ever mix into a solution.
Got it.
However, by sheer coincidence, liquid A and liquid B possess the exact mathematically identical density. They weigh the exact same amount per milliliter.
This is the trap.
If you pour them both into a separating funnel, what happens? How do the layers form?
They don't. The layers do not form at all. The separating funnel would be completely paralyzed.
Wait, if they refuse to mix, they have to go somewhere, right? Why would they just stack on top of each other?
Because stacking requires a vertical hierarchy dictated by gravity and buoyancy.
Gravity pulls downward on all matter.
Right. But buoyancy dictates that a denser fluid will sink and physically push a less dense fluid upward. If liquid A and liquid B have the exact same density, gravity pulls on them with the exact same force.
And neither has the buoyant power to displace the other.
Exactly.
So what does it look like inside the glass?
It would look like chemical chaos. You would likely see a bizarre stagnant suspension. Depending on the surface tension, you might have giant free-floating globs of liquid A hovering motionless inside liquid B.
They wouldn't rise, they wouldn't sink.
Or they might organize vertically, sitting side by side like pillars in the glass.
So the tool is rendered completely useless. You cannot drain one out the bottom without taking the other with it.
It perfectly demonstrates that our scientific tools are slaves to physical properties. A separating funnel doesn't separate liquids because it's magic. It separates them by exploiting a density differential.
If you remove the physical difference, the tool fails entirely.
Yes.
This leads us perfectly into the most complex problem of our deep dive. What happens when the physical differences are incredibly subtle?
That's where things get tricky.
What if the mixture isn't just two clear liquids? What if it's a highly complex, delicate biological or chemical mixture containing 5, 10, or 20 different compounds?
Like what?
Let's take the green pigment in a crushed spinach leaf, or the black ink in the pen sitting on your desk right now.
Okay. Good examples.
We can't boil black ink in a distillation flask. We just scorch the dyes and ruin them.
Right.
We can't use a separating funnel because the dyes are all dissolved in the same water. Gravity and heat are too blunt. We need a scalpel.
We need paper chromatography.
Paper chromatography.
It is a remarkably elegant analytical technique that relies not on gravity or heat, but on the delicate, invisible forces of molecular attraction.
I want to look at the etymology of the word because it basically gives away the secret. Chromatography is derived from two Greek roots. Chroma, meaning color, and graphene, meaning to write. Color writing.
It was originally developed by botanists to separate complex plant pigments, and color writing is a literal description of what the technique produces.
It forces hidden colors to reveal themselves by painting a pattern on a piece of paper.
Let's use the black ink from a standard sketch pen as our example.
Okay, to the human eye, black ink is just a single, dark substance.
But functionally, black ink is almost always a carefully engineered mixture of bright red, blue, yellow, and green synthetic dyes, all blended together in exact proportions so they absorb the entire spectrum of visible light, rendering it black to our eyes.
We want to tear that blackness apart to prove it's a mixture. How do we set up the color writing?
You start with a specialized, highly porous strip of filter paper. About an inch from the bottom edge of the strip, you draw a faint horizontal line with a graphite pencil.
Why pencil?
Pencil is crucial because graphite won't dissolve and ruin the test. Right in the center of that pencil line, you dab a single concentrated dot of your black ink. You let that ink dot dry completely.
Okay, the paper with the dry ink dot is our stationary phase. It just sits there. What does the move?
We use a solvent, which we call the mobile phase. For simple water-based inks, pure water is fine, though sometimes a 2% salt solution provides sharper separation.
Mm.
You pour a very shallow puddle of this solvent into the bottom of a glass beaker. Now you carefully lower the strip of paper into the beaker so that only the very bottom edge of the paper touches the puddle.
There is a critical experiment-ruining mistake that novices make here, right?
Oh, yes. The level of the liquid puddle must be physically below the pencil line and the ink dot.
What happens if it's not?
If you dip the paper too deep and the water immediately floods over the ink dot, the dyes will instantly bleed and dissolve out into the puddle at the bottom of the beaker. The mixture is lost into the bulk liquid and the experiment is dead.
So the ink must remain dry above the waterline.
Yes. So the bottom edge touches the water. Now the physics of capillary action takes over.
The filter paper is made of woven cellulose fibers, which act like a microscopic network of tubes.
Right. And through the forces of adhesion and cohesion, the water literally defies gravity, creeping slowly up the paper strip, moving higher and higher.
This upward movement of the solvent is the engine of chromatography.
As that rising tide of water reaches the pencil line, it washes over the dried black ink dot.
And the water acts as a solvent, redissolving the various dye molecules that make up the ink and begins dragging them upward along the paper.
But the dyes don't all move at the same speed. This isn't a team sport.
Far from it. It is an intermolecular tug-of-war.
Exactly. And this is the heart of the separation mechanism. Every individual dye molecule in that ink mixture is being subjected to two competing forces.
The moving water, the mobile phase, is trying to pull the dye upward.
But the cellulose fibers of the paper, the stationary phase, are chemically sticky. They are trying to grab onto the dye molecules and hold them in place.
And different dyes have different chemical affinities.
Right. Some dye molecules are highly polar and love the water. They have a strong affinity for the mobile phase and practically ignore the sticky paper.
Because they ignore the paper, those highly soluble dyes get swept up in the current and travel very fast, riding near the very top edge of the advancing water line.
But other dyes in that exact same black dot have a strong chemical affinity for the cellulose fibers. They stick to the paper.
The water struggles to drag them along.
Because they're constantly snagging on the paper fibers, they move much slower, lagging far behind.
So you walk away for 20 minutes. When you come back, the water has crept near the top of the paper. You pull the strip out.
And what was once a single, dense black dot on a pencil line has been stretched into a vertical rainbow.
You might have a sluggish smear of yellow ink hovering just above the starting line, a few inches higher, a distinct band of magenta, and racing at the very top, a bright stripe of cyan blue.
You have completely deconstructed the black mixture into its fundamental components based entirely on molecular friction.
It is profound because it reveals the hidden complexity of the everyday world.
And the beauty of chromatography is its accessibility. A listener could pause this, grab a coffee filter, a glass of water, and a marker, and perform advanced analytical chemistry right on their kitchen counter.
You can crush up the candy shell of an M&M, dissolve it in a drop of water, and use a coffee filter to see exactly how many different artificial dyes were mixed to create that specific color.
It turns the mundane world into a laboratory.
But as we move into the final stages of our deep dive, I want to leave the delicate world of chromatography behind and look at some extreme physical manipulations.
Let's do it.
I want to talk about bypassing the normal laws of thermodynamics and weaponizing raw physical force. Let's start with bypassing states of matter. There is a mixture mentioned in our outline. Common sand mixed with camphor.
Camphor is a highly unique organic compound. It's a white, waxy solid, often used in traditional medicine and religious rituals. It has an incredibly sharp, penetrating aroma.
If you grind camphor crystals into common beach sand, you have a solid, solid heterogeneous mixture.
It's just two piles of rocks mixed together.
You can't put it in a separating funnel. Water won't help if both are insoluble. How do you separate them?
You exploit camphor's thermodynamic superpower. Camphor undergoes a rare physical phase transition called sublimation.
Sublimation.
For most solid matter on Earth, if you apply heat, it follows a standard progression. The solid melts into a liquid puddle, and if you keep heating it, that liquid boils into a gas.
Ice melts to water, water boils to steam.
But camphor breaks that rule entirely.
Now,
Because of the specific vapor pressure of camphor molecules at atmospheric pressure, when you gently heat a camphor crystal, it completely skips the liquid phase. The molecular bonds shatter, and the solid crystal instantly flashes into a highly pungent vapor.
so to execute the separation, you put the mixture of sand and camphor into a shallow ceramic evaporating dish.
Right.
You take a glass funnel, flip it upside down, and place it directly over the pile of sand like a glass tent.
You plug the narrow stem of the funnel with a wad of cotton so nothing can escape out the top. Then you place a burner under the ceramic dish.
The heat transfers through the dish. The sand, which is essentially crushed quartz, has a melting point of over 1600 degrees Celsius.
At gentle heat, the sand does absolutely nothing. It just gets warm.
But the camphor reacts violently.
The camphor crystals heat up, hit their sublimation point, and instantly vaporize. The dish fills with invisible camphor gas.
Because gas expands, it rises upward into the narrow neck of the inverted glass funnel.
But the top of the funnel isn't near the burner. It is exposed to the cool air of the laboratory.
And that is the second half of the magic trick.
When that hot camphor vapor hits the cool glass walls in the upper neck of the funnel, it instantly loses its thermal energy. It undergoes deposition, which is the exact reverse of sublimation.
The gas molecules skip the liquid phase again and instantly crystallize back into a pure, solid, white, snowflake-like crust clinging tightly to the inside of the glass.
It is an incredibly elegant closed loop.
You turn off the heat, lift the funnel away, and you have perfectly pure, solid camphor stuck to the glass and perfectly clean, dry sand left in the dish below.
You bypass the liquid state entirely to achieve separation. That is chemical elegance.
But now let's look at brute physical force. What if we have a mixture where the particles are so incredibly tiny that gravity refuses to pull them down, but so heavily suspended that we can't filter them out?
This brings us back to the medical example we used at the very beginning of the show. Blood.
Human blood is a complex, heterogeneous suspension. You have dense red blood cells, slightly lighter white blood cells, and platelets, all floating in a watery, protein-rich liquid called plasma.
If a doctor suspects a patient has a severe infection or a blood-borne parasite like malaria, they often don't want to look at the whole blood.
They need to test the clear plasma, or they need to isolate a concentrated pellet of the red blood cells.
But if you draw a vial of blood and just set it on a table, gravity is painfully slow.
It might take many hours or even a full day for the heavy red blood cells to finally settle to the bottom of the tube.
And in emergency medicine, a 24-hour wait is a death sentence. Doctors need that blood separated in 3 minutes.
To achieve that, we cannot wait for Earth's gravity. We have to artificially amplify gravity by weaponizing inertia and circular motion.
We use a centrifuge.
The physics of a centrifuge are visceral. Anyone who has played on a playground understands it. Imagine two adults linking hands, leaning back, and spinning around in a circle as fast as they can.
The moment you start spinning, you feel a massive, invisible force trying to rip your hands apart.
You feel your body being violently pulled outward, away from the center of the spin.
That sensation is often called centrifugal force, though a physicist would clarify it's actually the inertia of your body trying to travel in a straight line while your arms constantly yank you into a circle.
Regardless of the semantic physics, the outward force is tremendous. A laboratory centrifuge harnesses that exact force.
You take the small glass tube of whole blood and place it into an angled metal holder on a motorized rotor. Then you slam the lid shut and spin that rotor at thousands of revolutions per minute.
The G-forces generated inside that spinning tube are immense, hundreds or thousands of times stronger than Earth's gravity.
Inside the tube, the heaviest, densest particles, the red blood cells, experience the most extreme outward momentum. They are violently hurled away from the center of rotation, smashing into the very bottom of the test tube and packing tightly together into a dense red pellet.
The lighter white blood cells form a thin microscopic layer right on top of them, often called the buffy coat.
And the lightest component of all, the watery plasma, cannot fight its way past the dense wall of cells below it, so it is forced to remain floating on top.
After just a few minutes of intense spinning, the motor brakes to a halt. You pull the tube out, and the chaotic, uniform red mixture has been brutally forced into distinct layers.
A dark red, solid pellet at the bottom, and a clear, yellowish column of pure plasma on top. The doctor can immediately pipette off the plasma for rapid biochemical testing.
It is a triumph of mechanical engineering. But here's where the story hits a wall. High-speed electric centrifuges are expensive pieces of precision machinery.
They require heavy metal rotors perfectly balanced to prevent them from vibrating apart at 10,000 RPM.
They require delicate electric motors. And most importantly, they require a constant, reliable supply of electricity.
Which is a luxury that much of the world does not have. If you are a doctor running a pop-up clinic in a rural off-grid village battling an outbreak of malaria, a $5,000 electric centrifuge sitting on your table is a useless paperweight.
You cannot separate the blood.
Which means you cannot definitively diagnose the disease, which means you cannot treat the patient. The technological bottleneck costs lives.
Which brings us to one of the most incredible feats of frugal bioengineering I've ever heard of.
This is such a cool story.
To solve this exact problem, researchers, specifically a team out of Stanford, led by Manu Prakash, looked away from high-tech motors and looked closely at a traditional children's toy.
A whirligig.
A whirligig is ancient. It is simply a flat disc, maybe made of wood or bone, with two small holes drilled near the center. You thread a loop of string through the holes.
By rhythmically pulling the ends of the string outward, the string twists and untwists, causing the disc in the middle to spin rapidly back and forth.
It's a noisemaker for kids. But the engineers put this toy under high-speed cameras and analyzed the rotational mechanics.
They realized that the physics of the twisting string acting on the disc was incredibly efficient at translating a slow, linear pull into mind-boggling rotational velocity.
They decided to adapt the toy into a medical device. They created the paperfuge.
The engineering is breathtakingly simple. They took two small discs of waterproof paper. They used tape to secure tiny sealed glass capillary tubes, each containing just a single drop of a patient's blood between the paper discs.
They threaded a specialized high-tensile string through the center holes, added two wooden handles to the ends of the string, and handed it to a human being.
And the results absolutely shattered expectations.
By simply pulling the handles in a rhythmic accordion-like motion, a human being, using zero electricity, can spin that little paper disc up to 125,000 revolutions per minute.
Let me contextualize that number. 125,000 RPM generates an outward centrifugal force equivalent to 30,000 times the force of Earth's gravity.
That is insane.
It is faster than many commercial electrified centrifuges used in state-of-the-art hospitals.
That sheer massive force cleanly and perfectly separates the red blood cells from the plasma in the capillary tube in exactly 90 seconds.
And it is made of paper, string, and tape. It weighs 2 grams. It costs roughly 20 cents to manufacture.
You can fit 20 of them in your pocket and carry them to any remote jungle clinic on Earth.
The paperfuge proves that high-end, life-saving diagnostic science doesn't always require expensive, fragile machinery.
Sometimes, a profound understanding of fundamental rotational physics, combined with the humility to learn from a children's toy, can completely democratize global healthcare.
It is an absolute masterpiece of separation science.
It truly is. But to conclude our deep dive, we must confront the final and perhaps most frustrating mixture of all.
We've used heat, density, paper fibers, sublimation, and 30,000 Gs of centrifugal force.
But what if you face a scenario where you have absolutely none of those tools? You're standing by a riverbed holding a beaker of incredibly muddy water.
Muddy water seems so simple, but it is chemically stubborn.
The dirt particles are so incredibly fine, so microscopic, that they just hover endlessly in the water, turning it into an opaque brown soup. Earth's gravity isn't strong enough to pull them down.
You try pouring it through a paper filter, but the dirt particles are so small they just wash right through the pores in the paper.
You don't have a $5,000 electric centrifuge, and you don't even have a 20-cent paperfuge. You just have brown water. How do you force the dirt to drop?
To solve this, we have to understand why the dirt refuses to settle. It isn't just about weight, it is about invisible force fields.
The force fields.
Microscopic dirt and clay particles suspended in water are subject to intense random collisions from the water molecules, that Brownian motion we discussed earlier. But more importantly, these specific clay particles often carry a net negative electrostatic charge on their surfaces.
And basic physics dictates that, like, charges repel.
Exactly. Every single speck of dirt in that beaker is encased in a tiny negative magnetic force field.
As two dirt particles drift toward each other, their negative force fields clash, violently repelling them away from each other.
They constantly bounce around the beaker, completely unable to touch or clump together. Because they can't clump, they remain microscopic.
Because they remain microscopic, they remain too light for gravity to pull down. They are locked in a permanent hovering dance of repulsion.
So to clean the water, we have to turn off the force fields. We have to neutralize the negative charge.
We achieve this through a chemical intervention called coagulation. We introduce a chemical coagulant that will short-circuit the repulsion.
A very common, globally utilized, and inexpensive chemical for this is powdered alum, which is known locally in many parts of South Asia as fitkari. Alum is a chemical compound rich in aluminum ions.
And aluminum ions, when dissolved in water, carry a massive positive charge, specifically a +3 charge.
The moment you drop a pinch of powdered alum into that beaker of muddy water and stir it, you are unleashing millions of highly positive chemical bullets into the suspension.
Opposites attract. The massive positive charge of the dissolved aluminum ions aggressively seeks out the negative surface charges on the floating dirt particles.
The aluminum acts like an electrical sponge. It swarms the dirt particles and completely neutralizes their negative force fields.
Once those negative repulsive fields are neutralized, the physics inside the beaker fundamentally change.
The dirt particles no longer repel each other. Now, when the random motion of the water pushes two dirt particles together, they actually touch.
And when they touch, weaker natural attractive forces, van der Waals forces, take over, acting like a chemical glue.
They stick together. Two tiny particles become one larger particle. That larger particle bumps into another, and they merge.
This cascading process of clumping is coagulation, often moving into a phase called flocculation, where you can actually see the dirt forming these fluffy, snow-like masses in the water.
And once those clumps, those flocks grow large enough, they finally cross the threshold of mass. They become too heavy for the water molecules to support them.
Gravity reaches out, grabs the heavy clumps, and pulls them down in a process called sedimentation. They sink like stones.
You wait 10 minutes, and the transformation is complete. You have a thick, dense layer of brown mud packed tightly at the bottom of the beaker, and resting gently on top of it is perfectly clear, transparent, drinkable water.
You simply tip the beaker and decant, or carefully pour off the pure water into a clean cup.
And while a single beaker of muddy water is a great visual, we must scale this concept up to truly appreciate it.
This exact chemical choreography, dumping massive amounts of coagulants like alum or iron salts into huge churning vats of murky river water to force the contaminants to clump and sink, is the primary mechanism used in enormous municipal water treatment plants worldwide.
It is how megalopolises purify billions of gallons of drinking water every single day.
It is the chemistry of survival. And that brings us full circle on our expedition today. We started by questioning the visual deception of a glass of milk, unmasking the Tyndall effect.
We explored how the exact molecular ratio, the concentration, determines whether an ORS packet saves a life or a pesticide destroys an ecosystem.
We analyzed the slow, geometric perfection of crystallization, a thermodynamic trick harnessed by ancient Indian salt makers.
We visualized the frantic thermal race of distillation, separating acetone on a lab bench and tearing apart crude oil in towering refinery columns to build our modern infrastructure.
We watched immiscible liquids fight for buoyancy in a separating funnel, and we used the capillary action of paper chromatography to deconstruct a single black dot into a hidden rainbow of chemical affinities.
We watched camphor completely bypass the liquid phase through sublimation, and we marveled at the 125,000 RPM generated by a 20-cent paper toy to diagnose malaria.
Finally, we used the electrostatic warfare of alum coagulation to force mud to surrender to gravity.
We have covered an immense amount of physical and chemical ground, but there is a crucial pivot we need to make as we bring this deep dive to a close.
Throughout this entire journey, we have treated separation as a pristine scientific endeavor, something that happens in a clean glass beaker, a specialized centrifuge, or a highly engineered refinery.
But the reality is the ultimate, most existentially critical separation technique of the 21st century is not happening in a laboratory.
No, it needs to happen in our kitchens, our offices, and our city streets. I am talking about the macro-scale separation of our own creation, environmental waste segregation and recycling.
Human civilization is currently producing an unfathomable, accelerating tsunami of mixed waste. We throw plastics, glass, heavy metals, toxic batteries, cardboard, and rotting organic matter into a single bin.
If we just dump that entire heterogeneous nightmare into a landfill, it is toxic, useless, and ecologically devastating.
The landfill is the ultimate chaotic mixture, but if we apply the philosophical lessons of everything we've just discussed, if we invest the time, the energy, and the infrastructure to systematically untangle that mixture, we fundamentally change the paradigm of human existence.
Proper waste segregation relies on the exact same principles we just spent an hour deconstructing, isolating the valuable raw materials from the chaotic jumble.
We have to act like the fractional distillation column. We have to separate the pure, infinitely recyclable aluminum from the compostable organic sludge.
We have to isolate the glass so it can be melted back into perfectly pure silica structures. We have to strip the rare earth metals out of old smartphones so they can be fed back into the industrial system.
It is the only mathematical way to build a sustainable, circular economy that doesn't consume the planet.
We have spent centuries mastering the separation of the natural world to build our civilization. The next century must be defined by our ability to separate the synthetic world to save it.
Which brings me to a final provocative thought I want to leave you with.
Tomorrow, when you are standing in your kitchen, holding an empty plastic bottle in one hand and an apple core in the other, and you make the conscious, meticulous choice to sort them into their correct respective bins.
I want you to pause and realize what you are actually doing in that moment. You are not just doing a mundane household chore.
By making that choice, you are essentially acting as a giant, human-powered separating funnel for the Earth. You are doing at a macro level exactly what the brilliant chemist does at the micro level.
You are actively, physically fighting back against the relentless entropy of a mixed-up universe, preserving the pure, valuable resources that our entire collective future depends on.
Keep fighting the chaos, keep questioning the mixtures around you, and we will see you on the next deep dive.